Good morning, students. I am Navdeep Dhaliwal, faculty of RI College of Engineering and IT, Electronics and Communication Department. Today we will discuss about the luminance signal. So these are my session outlines. First we will study about luminance or brightness, and then color voltage amplitude, and then Y signal amplitude, and then production of color difference voltage, and at the end we will discuss about compatibility considerations. So let us start this session with first agenda, that is luminance or brightness. So this is the amount of light intensity as perceived by the eye regardless of the color. In black and white picture, better light and parts have more luminance than the dark areas. Different colors also have shades of luminance in the scene that enough equally illuminated appear more or less bright as indicated by the relative brightness corresponds curve of figure. Thus on a monochrome TV screen, dark red color will appear as black, and yellow as white, and a light blue color as gray. So we can see in the figure wavelength of different colors versus sensitivity of the eye. So we can observe the sensitivity of green color, that is maximum as compared to other colors. To generate the luminance of bright signal that represents the luminance of the scene, the three camera outputs are added through a resistance matrix in the proportions of zero point 0.3, 0.59 and 0.11 of red, green and blue respectively. This is because with white light, which contains the three primary colors in the above ratio, the camera output were adjusted to give equal voltages. The signal voltage that develops across the common resistance RC represents the brightness of the scene and is referred to as Y signal. Therefore, the luminous signal Y is equal to zero point 0.3 R plus 0.59 G and 0.11 blue. So, in figure A illustrates the nature of output from the three cameras when a horizontal line across a picture have vertical bars of red, green and blue color is scanned. Note that at any one instant only one camera delivers output voltage corresponding to the color begins scanned. In figure B, different values of red color voltage are illustrated. Here the red, pink and pale pink, which are different shades of red having decreasing value of color intensity. Therefore, the corresponding output voltages having decreasing amplitudes. Thus, we can say that uh, red, green and blue voltage indicates information of the specific color, while their respective amplitudes depends on the level of saturation of that color. Next, consider the scanning across a picture that has yellow and white bars besides the three pure color bars. The voltage of the three camera output are drawn below the camera bar pattern in figure. Notice the value shown for yellow as an example of complementary color, since yellow includes red and green. Video voltage is produced for both these primary colors. Since there is no blue in yellow, the blue camera output voltage is at 0 for the yellow bar. The white bar at the right includes all the three primary colors, and so all the three cameras develop output voltage when the bar is scanned. As already states, the Y signal contains brightness variation of the picture information and is formed by adding the three camera outputs in the ratio Y is equal to 0.3 R plus 0.59 G plus 0.11 B. These percentages corresponds to the relative brightness of the three primary colors. Therefore, a scene reproduced in black and white by the Y signal looks the same as when it is televised on monochrome. Figure on the next slide illustrates how the Y signal voltage is formed from the specified proportions of red, green, and blue voltages for the color bar pattern. Notice that Y signal for white has a maximum amplitude because it includes red, green, and blue color. For the other bar, the magnitude of Y decreases or changes in accordance with the color or color that form the bars. All the voltage values can be calculated as illustrated by the right up below figure if only this Y signal is used to reproduce this pattern. It will appear as monochrome bar shading off from white at white at the left to gray in the center and black at the right. Their value corresponds to the staircase pattern of Y voltage shown in the figure. Notice the progressive decreases in voltage for the relative brightness of the various color bars. So you can see in the figure where formation of luminance Y video signal with the resistance matrix from color camera output. Note that yellow appears 89% brightness as compared to 100% of white. Similarly, cane, green, magenta, red and blue appears 70%, 59%, 41%, 30%, and 11% bright, respectively, as compared to assume 100% brightness for white. So the production of color difference voltages, the Y signal is modulated and transmitted as is done in a monochrome television system. However, instead of transmitting all the three color signals separately, the red and blue camera output are combined with the Y signal to obtain what is known as color difference signals. Color difference voltage are derived by subtracting the luminance voltage from the color voltage. Only red minus yellow and blue minus yellow are produced. It is only necessary to transmit two of the three color difference signals, since the third may be delivered from the other two. So the production, this is the figure showing production of color difference voltages. So the voltage Vg is obtained from the resistance matrix is low because Rc is chosen to be small to avoid crosstalk. Hence, it is amplified before it leaves the camera subchassis. Also, the amplifier Y signal is inverted to obtain minus Y as the output. This is passed on to the two adder circuits. One adder circuit adds the red camera output to minus Y to obtain the R minus Y signal. Similarly, the second adder combines the blue camera output to minus Y and delivers B minus Y as its output. So this figure shows production of luminance, and color difference signals. Note that the y is equal to 0.3R plus 0.59G plus 0.11 B, and the color difference R minus Y is equal to 0.7 R minus 0.59G minus 0.11 B, and B minus Y is equal to 0.89 B minus 0.59 G minus zero point 0.3 R. So compatibility considerations, the color difference signals equal 0 when white or gray shades are being transmitted. This is illustrated by two examples. So let us assume red, green and blue voltage is equal to 1 volt. Then we put the value of red, green and blue in Y, so we get the voltage is equal to 1 volt. So in when we put this value in color difference R minus Y, then we will get 0 volt, and when we put this value in B minus Y, then we get the voltage 0 volt. In first case we can see when red, green and blue is equal to 1, then the luminance signal is 1 volt and R minus Y is 0 volt and B minus Y is 0 volt. And the case B, let us assume when R is equal to G is equal to V is less than 1, then when the value of V is put in the Y signal, then we get the luminous signal is equal to V volt, and the color difference R minus Y is 0 volt, and the color difference B minus Y is 0 volt. So we can see these two cases when the value of three colors is equal to 1 volt and the value of three colors is less than 1. Thus it is seen that color differences signals during the white or gray content of a color seen of during the monochrome transmission completely disappear, and this is an adds to compatibility in color TV system.